Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about properties of covariance. And the first property of the covariance is if capital X and capital Y are two random variables, then the covariance is covariance of x comma y or sigma suffix xy is equal expectation of xy minus expectation of x into expectation of y. So prove this property. Now next coming to the proof. So we know that the covariance between two random variables is denoted by sigma suffix xy or covariance of x comma y. The covariance between two random variables is given by covariance of x comma y is equal expectation of x minus mx into y minus my. So now here, since mx is the expected value of the random variable x, m suffix is the expected value of the random variable y. So multiplying these two terms, multiplying x minus mx into y minus my, we get four terms. So that are x into y minus x into my minus y into mx minus into minus plus mx my. So using property of the expectation, so expectation of sum of random variables is equal to sum of their individual expectation. So using that property on RHS side of this equation, applying expectation into each term, we get so covariance of x comma y is equal expectation of xy minus expectation of x into my. So my is the expected value of the random variable y. So this my is also denoted as expectation of y minus expectation of y into mx. So mx is the expected value of the random variable x and it is also denoted as expectation of x plus expectation of mx my. So mx my are the constant using the property of the properties of expectation. Expectation of mx my is the mx my. So mx is the expected value of the random variable. It is also represented as expectation of x. My is the expected value of the random variable and it is also represented as expectation of y. So that is expectation of x, expectation of y. So on RHS side, minus expectation of x, expectation of y plus expectation of x, expectation of y is cancelled. And the remaining RHS term is covariance of x comma y is equal expectation of xy minus expectation of x, expectation of y. So this is the first property proof. So we know that the correlation between the two random variables is given by r suffix xy is equal to expectation of xy. So expectation of xy is the correlation between two random variables and it is denoted as r suffix xy. So the RHS term of this equation is also written as sigma suffix xy is equal rxy minus expectation of x, expectation of y. Since capital X and capital Y are the independent random variable, the condition of the independent random variables of the expectation is expectation of xy is equal expectation of x into expectation of y. So capital X and capital Y are the independent random variable. Expectation of product of random variables is equal to product of their individual expectation. That is expectation of xy is equal expectation of x into expectation of y. Applying this condition into this equation, we get covariance of x comma y is equal expectation of xy is expectation of x into expectation of y. So on RHS side plus expectation of x, expectation of y minus expectation of x, expectation of y is cancelled. So the remaining RHS term is 0. So capital X and capital Y are the independent random variables, then the covariance of x comma y is equal to 0. So this is the first property. And one more property, if x and y are the independent random variable, then the covariance of x comma y is equal to 0 is the one more property of the covariance. And second property is for two random variables, capital X and capital Y are the two random variables, then variance of x plus y is equal variance of x plus variance of y plus 2 covariance of x comma y. and variance of x minus y is equal variance of x plus variance of y minus 2 covariance of x comma y. This is the second property. So this property is already explained in the concept of variance. So next, coming to the proof, consider two random variables capital X and capital Y. So we know that variance of x is equal to expectation of x square minus expectation of x whole square. So first we want to prove that variance of x plus y is equal to this one. So this is the variance of x expression. In this expression, x is substituted by x plus y. The variance of x plus y is equal expectation of x plus y whole square minus expectation of x plus y whole square. In this expression, x is substituted by x plus y. We get expectation of x plus y whole square minus expectation of x plus y whole square. So now here in this first term, first applying the a plus b whole square expansion, and the second term, first applying the expectation into each term. Using property of expectation, expectation of x plus y is expectation of x plus expectation of y. And the first term applying a plus b whole square expansion, expectation of x square plus y square plus 2xy, that is the first term, minus, and the second term within the bracket term, first applying the property of expectation. That property of expectation is expectation of x plus y is equal to expectation of x plus expectation of y. And this first term applying expectation into each term using the property of the expectation of sum of random variables is equal to sum of their individual expectation. First term applying the expectation into each term, and the second term applying a plus b whole square expansion. So we get expectation of x square plus expectation of y square plus 2 expectation of xy minus, and the second term applying a plus b whole square expansion, expectation of x whole square plus expectation of y whole square plus 2 expectation of x expectation of y. And second term multiplying minus within the bracket term, we get variance of x plus y is equal, okay, at the same time, okay, applying minus into plus minus, minus into plus minus, minus into plus minus. At the same time, RHS of this term is also arranged as expectation of x square minus expectation of x whole square plus expectation of y square minus expectation of y whole square plus 2 expectation of xy minus 2 expectation of x expectation of y. So using definition of the variance, what is the definition of the variance? Expectation of x square minus expectation of x whole square is variance of x. So using this expression, the RHS term of this equation is this within the bracket term is variance of x, and this within the bracket term is variance of y. So 2 into this within the bracket term is covariance of x comma y. So therefore variance of x plus y is equal variance of x plus variance of y plus 2 covariance of x comma y. Similarly, prove that variance of x minus y in the same process. In this equation, substitute x is equal to x minus y. In the same process, we can prove that finally we get variance of x minus y is equal to variance of x plus variance of y minus 2 covariance of x comma y. If the random variables capital X and capital Y are the independent random variable, the independent random variable condition is expectation of xy is equal to expectation of x expectation of y, and the random variables x and y are independent random variable. The covariance between two random variables is equal to 0. So that is covariance of x comma y is equal to 0. Applying this condition into this expression and this expression, we get variance of x plus or minus y is equal to variance of x plus variance of y. This is the second proof of property. So this property is already explained in my previous videos. That is concept of variance properties. The next property is if x and y are two random variables, then the covariance of x plus a, y plus b, then the covariance of x plus a, y plus b, where small a and small b are the constant. So covariance of x plus a comma y plus b is equal to covariance of x comma y. So now coming to the proof, we know that. So what is the definition of the covariance between two random variables? Covariance of x comma y is equal to covariance of x comma y is equal to expectation of x minus expectation of x into y minus expectation of y. So this is the covariance between two random variables definition. Now here we want to prove that covariance of x plus a comma y plus b is equal to covariance of x comma y. In this definition, x is substituted by x plus a, y is substituted by y plus a. We get LHS term is covariance of x plus a comma y plus b. On RHS side, so x is substituted by x plus a, y is substituted by y plus b. We get expectation of x plus a, x plus a whole bar. So now here this expectation of x is also denoted as x bar. Expectation of y is also denoted as y bar. So x plus a whole bar, expectation of y is y plus b whole bar, or otherwise this x plus a whole bar is also written as expectation of x plus a. This y plus b whole bar is also written as expectation of y plus b. So covariance of x comma y is equal. So using properties of expectation of x plus a is expectation of x plus a. Here also using property of the expectation of y plus b is expectation of y plus expectation of b. So expectation of b is b. So now here before minus is there, multiplying minus within the bracket term. Here also before minus is there, minus multiplying minus within the bracket term. We get expectation of x plus a minus expectation of x is also denoted as mx. So minus into plus minus a, y plus b minus expectation of y is also denoted as my, minus into plus minus b. So now here plus a minus a is the cancel, plus b minus b is the cancel. So therefore covariance of x plus a comma y plus b is equal expectation of x minus mx into y minus my. So the RHS term is the covariance between two random variables, that is covariance of x comma y. And this is the third property. Next, fourth property is if capital X and capital Y are two random variables, then the covariance of ax comma by is AB covariance of x comma y, where small a and small b are the constants. So now coming to the proof, we know that consider two random variables x and y. The covariance between two random variables is covariance of x comma y is equal covariance of x comma y is equal expectation of x minus e of x, y minus expectation of y. So this is the covariance of x comma y. So in this definition, now here x is replaced by ax, y is replaced by by. We get covariance of ax comma by is equal expectation of ax minus expectation of ax into by minus expectation of by. So using properties of expectation of ax is a into expectation of x. Similarly, expectation of by is b into expectation of y. Okay. So therefore, expectation of ax minus a expectation of x into by minus b expectation of y. Now here within the bracket term, from these two terms, a is the common. and these two terms b is the common. So using properties of expectation, expectation of ax is equal to a expectation of x. So using that property, the RHS term is written as ab is the constant, ab into expectation of x minus e of x into y minus e of y. So this is this term is covariance between two random variables. So therefore, covariance of ax comma by is equal ab covariance of x comma y. So these are some important properties of covariance of the random variables x and y.